My name is Steve Strength. I'm a traffic engineer and the co-chair of the New Orleans Regional Traffic Safety Coalition. I have 31 years of experience as a traffic engineer with the Louisiana Department of Transportation and Development, and I've been involved in the Traffic Safety Coalition for a number of years as well. We work with police officers, public works representatives, and other safety advocates on safety topics of interest to the public and the private sector. One of the safety initiatives that we've been working on in the coalition is looking at features of yellow light timing as they relate to safety, as well as the application of automated red light enforcement. We became interested in this because there have been a number of changes in the way that drivers react to yellow lights, and there's been a great deal of concern expressed because of the proliferation of red light cameras and camera enforcement systems in the New Orleans area. We wanted to do a little bit more practical investigation and find out what the implications of these systems really are, and whether the formulas that engineers use to calculate yellow light timings were still realistic or correct for the conditions that we see today. In order to give some clarity to the problem of yellow light timing, we developed this chart, and it has several components to it. One of the first things you need to be able to figure out when looking at yellow light timing is how much distance it takes for a vehicle to come to a full stop. The formula that engineers use is a basic physics formula for S, which is distance, and it is S equals VT plus V squared over 2A, as shown here. The S is for stopping distance in feet, the V is for vehicle speed in feet per second, so that, for instance, 40 miles per hour would be 58.8 feet per second. The T is the perception reaction time, which we'll talk about a little bit more later. And A is the acceleration, or in this case, deceleration rate, which is assumed for this case to be 10 feet per second per second. So by calculating S equals VT plus V squared over 2A and plugging in the values, for 40 miles an hour, 58.8 feet per second, square that, and then divide 2 times 10 feet per second squared gives you a total stopping distance of 172.8 feet, and by adding in an additional second of distance for the perception reaction time, we get a total stopping distance, including the perception reaction, of 231.6 feet. So that is the total distance for braking the vehicle from a speed of 40 to 0, as well as adding in the reaction time. Now the T that I mentioned, the time that it takes to initiate the stop, is really when the driver is deciding whether they're going to stop or not. As you approach a red light, you have to make a decision based on your speed and your distance from the intersection, whether you believe that it's safe or practical to stop. And that decision process is what calculates into the perception reaction time. Now there's actually more than just the basic deceleration formula to this from the physics. There's actually a way to calculate a deceleration from one speed to another, which is a much more complex formula. But since our final speed in this case is 0, we have the simplified version as shown here. According to most of the guidance given by the Institute of Transportation Engineers and other technical groups, the assumed perception reaction time is 1 second. This has been used for many years. It's generally accepted in the engineering community, but there has been significant discussion recently about whether that is still a good number. But for our example, it is 1 second, at least for the time being. Now, just showing graphically what this means is, we have, if a vehicle is traveling at 40 miles per hour, it takes 58.8 feet to travel the first second, and that is the perception reaction time, followed by a successive series of seconds as the vehicle slows. So at a deceleration rate of 10 feet per second squared, or 10 feet per second, after the first second, you're still going at 40 miles per hour because you just used up the 1 second of perception reaction time. After the second you have reduced your speed by 10 feet per second, so you're at 48.8, and you go down from there until you reach 0. The total time to actually stop using this is 6.8 seconds from 40 miles per hour as calculated from the formula. And that in that distance you cover the 231.6 feet that we calculated. The driver also has to have a feel for the deceleration distance that will be required for the vehicle to stop as he or she approaches the intersection. That is not something most drivers are thinking about before the light changes, although they may be expecting the light to change to yellow, especially if it has been green for some time. But they don't know how long the yellow light is actually going to be. They also don't necessarily know their actual speed when the light turns yellow, and they don't intuitively know the pavement conditions that may affect their ability to stop within that prescribed distance, as we talked about. However, the decision needs to be made to stop at the required stopping distance, and it has to be made at the time that is shown in the formula for this to work out correctly. The alternative is that the vehicle must be able to pass through the intersection before the signal turns red, if the driver decides not to stop. And in that case, he or she must be able to pass through the intersection safely before the cross street green is displayed. So a vehicle who decides not to slow down at this point would proceed at the speed of 58.8 feet per second or 40 miles per hour and continue through, and at that speed he would be able to actually make it into the intersection before the light turned red. Now, we've talked a little bit about stopping distance. The next formula is for the actual yellow light timing, and that is the time to stop as calculated from the ITE formula. It is derived from the distance formula, and it is the Y, or yellow light timing, is perception reaction time, what we talked about before, and plus the initial velocity or speed over 2 times the acceleration, or in this case the reduction in, by 10 feet per second squared. So from our previous example calculating Y, we still use 1 second for the yellow timing. We don't have to multiply that times velocity this time because we're simply calculating time. And then we add in the time to slow down to a stop, and that is from the initial speed, 58.8, divided by 2 times our assumed deceleration rate of 10 feet per second squared. So 58.8 over 20, and calculate that out and you get a total of 3.94 seconds. So the ITE formula, time to stop, is approximately 4 seconds. Now the total stopping maneuver takes a total time of 6.8 seconds to complete, as we've shown from the distance formula. But notice that the yellow light timing we calculate is not the same as the calculated time for the stopping maneuver based on the distance chart. The yellow light timing is not the full time that it takes to stop, but it's actually a warning interval, which should be equivalent to the time the driver has to have in order to decide to stop, which is perception reaction, and also for the time it takes the driver to begin decelerating within the distance and at the rate assumed in the formula. So the simplified formula of Y equals T plus V over 2A applies to time, but it is about 2.8 seconds shorter than the time that's calculated from the distance formula. Part of this can be explained because when a vehicle decides to stop back here, they would actually be stopping as the light turns red. In other words, the light would turn red before they get to the stopping point. But at that point, they've already decided to stop. Therefore, it's not a problem. But the problem comes in if they start to stop a little bit beyond, or they have some other problem or distraction involved in this, and they're not able to begin their maneuver right precisely at the point defined by the formula in the perception reaction time. Now, in connection with this, there are some points to ponder, and we've shown on the chart. The normal range of of yellow light timing that we use, which is calculated from the formula, varies maybe from 3 to 6 seconds, depending primarily on the approach speed that's used. At speeds above 30 miles per hour, even 6 seconds total clearance time may not be enough to stop. We can calculate that out based on the distance chart and show that even at 40 miles per hour, the time shown from the distance formula is 6.8 seconds. Interestingly though, most violations of the yellow change interval do not result in crashes. The reason for this is because the traffic on the cross street does not begin right at the end of the yellow light interval. There's typically a lost time that we figure. It could be up to 3 seconds for the drivers to react before they begin to enter the intersection on the conflicting approach. Now, as we talked about, the formula actually states this, but longer yellow interval times are needed for the higher approach speeds. And regardless of the posted speed limit, one of the things that traffic engineers should be doing is checking the actual approach speeds, typically an 85th percentile speed, that can be used to calculate that formula so that you're actually reflecting the behavior of drivers on that approach. Some studies have indicated that approach speeds can vary by as much as 7 to 10 miles per hour on typical urban arterial streets in signalized areas. So if the traffic engineer does not account for a higher approach speed and simply uses the speed limit, these stopping distances will be much longer, and the required stopping time would therefore also be much longer. So we need to account for that, and the only way really to do that is to use engineering judgment once the signal is put in operation, or using a better, using a more reliable measure such as the 85th percentile speed of the approach, rather than simply looking at the speed limit. Now, one of the things that's talked about in discussions of red light camera enforcement is use of the ITE formula as meeting standards. But in fact, the ITE formulas and the distance formula are guidelines that are required to be used by the federal standards, but they do not take the place of engineering judgment in determining whether the calculated yellow time is appropriate for the situation. There could be other things at play, such as the grade of the approach, which could require a longer yellow time, a larger percentage of trucks in the traffic stream, the friction of the pavement on the approach. If it's worn, it may take longer for vehicles to stop, and those types of things. And these are all items that need to be considered when looking at the engineering judgment side of the yellow light timing problem. Now there are some studies that might indicate that yellow times over 6 seconds may lead to increases in rear-end crashes because of variable speeds on the approach. And slower drivers may tend to react quicker to yellow times, whereas the faster drivers would need to use the entire 6 seconds or more to make their maneuver, and this could cause some rear-end crashes. This is also the case where drivers are super sensitive to the occurrence of the yellow light and may lead to rear-end crashes in the case of automated enforcement, because they may be more aggressive in trying to stop in order to avoid getting a ticket. And for that reason, there is some evidence that photo enforcement can lead to increases in crashes due to the fact that the driver focuses on the light and the changing of it, rather than on the traffic around him or her, rather than on other environmental factors such as wet pavement, perhaps even pedestrians in the path approaching the traffic signal. We want the driver to focus on everything that's around him and not have to completely focus on the signal changing in order to maintain the safest possible intersection operation. So having said that, let's take a look at a little bit more reality. I mentioned some of the factors that traffic engineers need to be using in addition to the guidelines that are contained in the ITE formula and the stopping formula. Now this chart on the right represents more of a true reality on the street, and what we've done here is simply increase the assumed perception reaction time by a half a second, only a half a second, to 1.5 seconds. Everything else in the formula remains the same. So our old formula for the, and this is for the stopping time, which is the ITE formula for yellow light timing, is that the yellow is perception reaction time plus the initial speed over the deceleration. And calculating that out, you would get a total time of 7.3 seconds in this case. Now the distance formula gives us a longer distance as well, because of, instead of only traveling 58.8 feet during the perception reaction, we now travel almost 30 feet farther before we start braking on the approach to this intersection. So the total, in this case, stopping distance is 261 feet. The total braking distance is the same, assuming the same factors that were in play at in the other case, of 172 feet roughly. But the additional time for perception reaction puts us well into the intersection at the time, or not quite into the intersection, which causes the driver to enter the intersection on the red light, because it takes them much longer to stop. In this case, you could almost say that the vehicles in this zone, which is after the light turns red, they're encountering a red light almost by design, because they cannot react quickly enough and bring their vehicle to a safe stop prior to entering the intersection. The reason we've marked this area in red is these are the vehicles that would be caught in the intersection because they're not able to stop prior to entering the intersection, even though they want to stop. Because of this additional perception reaction time, they are going to be entering the intersection on a red by design, because they were not able to react quickly enough and begin their stopping maneuver at the point that that was prescribed by the previous formula. If they decide to stop, they will still be traveling, in this case, about 20 to about 32 feet per second at the point where they come up to the stop bar, and would either have to continue through and try to continue to stop maybe in the middle of the intersection, or they may have to go ahead and try to accelerate to get through before the cross street green begins. In either case, that's not a safe situation. The real point of the safety has to be taking place back here in order to give the driver enough warning to be able to make the proper reaction and stop prior to entering the intersection. Now, a few factors to consider when we're talking about getting back to reality, and this is very important. Credibility with the public is very important. It is the key, in fact, to effective traffic control. We have a saying in the traffic business that traffic control is actually an oxymoron. We think that by putting signs or signals out that we're actually controlling the traffic. And in fact, what we are doing is giving motorists the information they need to safely operate their vehicles. But whether they take our advice, so to speak, is up to them. What we definitely don't want to do is entrap them and put them in a safe situation that causes them to make a risky maneuver or some other unsafe act. The only way to ensure that drivers will comply with our traffic controls is to have credibility and not put them in those situations, and not give them information that is either not relevant or is actually inaccurate for their situation. Many of the formulas and research that were done on developing the ITE formula were done many, many years ago, at a time when our driver population, our design of vehicles, and many other factors about the traffic stream were different than what they are today. So it's incumbent on engineers to take the lead and make adjustments to properly adapt for these different types of changing conditions. Setting standards for yellow light timing needs to include things like even driver distractions. We all know that today Drivers are bombarded with more information than ever before, and these distractions can also lead to a degradation of their ability to react to something as simple as a yellow light being displayed on the approach to an intersection. We would like to think that all drivers are aware and are paying attention in all cases to the possibility that the light may change, but that's simply not the case, and we need to accept that reality. And one of the ways that traffic engineers can adjust for some of these changing conditions, particularly known factors, and some of these maybe not so well known factors such as driver distraction, is to introduce the concept of longer yellow times. They can be and have proven to be an effective countermeasure to reducing red light violations as well as red light crashes, particularly right angle crashes, which tend to be one of the most severe types of crashes at intersections. There's been a lot of research and then a lot of empirical experimentation with longer yellows, and there have been cases where strong evidence is displayed for the effectiveness of even increasing by yellow timings by as little as a half second or up to 1 second, and seeing favorable results in the area of both violations as well as crash history. Another factor that traffic engineers can use to keep the yellow lights from becoming too long is to introduce an all red interval. We haven't talked a lot about that yet, but an all red interval is an extension of the yellow light change interval that basically gives drivers the ability to clear through the intersection after the light has turned red prior to the introduction of the cross street movement into the intersection. And this provides a factor of safety. It not only allows for the clearance of the traffic through the intersection, even if they enter on the yellow rather. If they enter on the yellow, they can continue to proceed through after it has turned red without fear of having the cross street hit them. But it also can allow for some variation in the ability of drivers to react if the yellow times become excessively long. And as we mentioned before, the preferred maximum yellow light time is about 6 seconds. And if you have to calculate a longer yellow than that, you can always introduce that red light, the red clearance timing into that to keep that from getting too long. Now, one of the points that needs to be emphasized is that red light camera enforcement, photo enforcement, should not be considered as a substitute for good traffic engineering practice. As we've discussed, there are a lot of things traffic engineers should and can do to improve compliance with yellow light timing and being able to stop on approaches. And those things should always be tried and experimented with or introduced into the mix prior to considering photo enforcement. Photo enforcement in some cases can be an effective countermeasure, but only after some of the other much less intrusive countermeasures have been attempted. Another factor that comes into play with photo enforcement is the tolerance that's given for the enforcement to be activated. Typically, a police officer will allow a tolerance of maybe a half to a full second prior to even considering giving a ticket for a red light violation. Part of this is because police officers, like traffic engineers, understand that there are variations in the traffic mix. There are conditions and distractions which may cause a motorist not to be able to react as quickly as they would like to. And not just inattention. It may be that they're pulling a trailer. It may be that they observe a heavy vehicle behind them that may not be able to stop, and so they continue on through the intersection. And those types of things are behavioral elements that a police officer on the scene can consider and make judgments about before issuing a red light violation ticket. Photo enforcement has no such judgment and has to be set at a threshold. But if it is done, it should be set at a threshold similar to the level of judgment that a police officer can exercise in those cases to prevent too many violations being issued and losing credibility with the public. Other countermeasures such as better signal visibility using backplates, better intersection definition using striping, and fewer distractions in the area of intersections such as unnecessary signing are factors that could reduce crashes without the need for photo enforcement. And again, like the traffic engineering methods we discussed and adjustment of the yellow light timing if necessary to meet conditions, these other factors should also be considered as countermeasures prior to the introduction of photo enforcement. One of the interesting things we looked at when we were doing our testing out at the State Police training facility was the right turn maneuver. And we actually did deceleration testing and speed testing for the right turn maneuver to see how that differed from the straight through maneuver that we've been talking about throughout this episode on our formula. You have to understand that the ITE formula was developed as far back as the 1950s, and it was basically designed only to deal with the straight through approach. And the people who developed that formula recognized that any variation of this, especially turning maneuvers to be made off of that straight through approach, would have to be adjusted, or the timing would have to be adjusted to accommodate those differing conditions. And that's part of what goes into a traffic engineer's engineering judgment to develop the yellow light timing. But the interesting things we noted about the right turn maneuver was that, first of all, the drivers in every case, regardless of the type of vehicle, began to slow down quite a ways away from the intersection, even though the light was still green. This was because they were preparing to make the maneuver and they had to slow down in order to start to observe some of the other factors that come into play when making a right turn maneuver. So the first thing that the driver considered was the need to slow down on approaching the turn, and then starting to scan for potential hazards as they got closer to the turn. Now, some of those things might be the actual condition, width of the roadway that they were turning into, the fact as to whether traffic was on that approach and might be encroaching into their path that they were intending to turn into. Probably one of the most important things is the presence of pedestrians or other hazards that might be encountered, and having to perhaps yield to a pedestrian that was in a parallel crosswalk. In every case, regardless of whether it was the 18-wheeler or the sedan, the turn was made at 12 miles per hour for this particular turn. Now, that may not be true for every turn, but every vehicle was turning at the same speed as they entered the intersection. At that speed, a driver who was faced with a red light would not be able to stop before entering the intersection. Now, in each of the cases that we tested on the approach, it took about 6.1 seconds to make the deceleration and approach the intersection down to 12 miles per hour. Since most yellow light timing in urban areas is set in the neighborhood of 4 seconds, it may be varying from 3 to 6 seconds, but in many cases it's 4 seconds, particularly at intersections that have red light enforcement cameras. Within that time that it takes to slow down, the 4 seconds would be expired before the vehicle was able to complete their maneuver turning into the intersection. And that could actually result in a red light enforcement ticket in that case. In this tape, we've talked a lot about different engineering formulas and facts, but I wanted to emphasize 10 points to kind of wrap this up and things to ponder about this whole yellow light timing issue. Number one, the yellow light formula does not give time to stop, it gives time to go. That is, it allows a motorist to clear the intersection without getting a red light ticket. Number two, at a speed of over 30 miles per hour, even 6 seconds of yellow time may not be enough to stop. Number three, red light violations in the first few seconds of red do not cause crashes normally because of the lost 3-second rule. That's the time that it takes to cross traffic to start up. Number 4, in calculating yellow light times, traffic engineering guidelines require using the 85th percentile speed, not the posted speed limit. Also, the addition of an all red interval can be an effective means of preventing crashes without having to resort to red light enforcement. Number 5, the ITE formula alone does not meet standards. It is up to the engineer to adjust for all possible safety issues. Number 6, the 1 second allowed perception and reaction time in the ITE formula appears to be outdated. And when drivers need more time, they will receive a red light ticket by design. There are many factors, as we've discussed, that can distract a driver or cause them not to be able to react within the 1 second period. Number 7, the ITE yellow light formula was designed for straight-through stopping only, because in the 1950s, a right turn on red was not allowed at all. Drivers were always required to come to a full stop and not to be able to turn right on red. Number 8, testing completed by DOTD traffic engineers at the State Police Training Facility demonstrated the requirement of more than 6 seconds to complete a turn on green or yellow. Number 9, intersections with cameras set with a 4-second yellow light duration will normally create a false right turn on red violation by design, again because of the requirement to take more time to complete a turn. Number 10, and perhaps most important, photo enforcement should never be used in place of good engineering practice.